right, today we have several more tests for convergence. And one of those tests for convergence that we're going to talk about today is called the direct comparison test. So we're going to talk about a series that has no negative terms. So this is not an alternating series. This is something that's only got positive terms. And what the direct comparison test says is that this series right here is going to converge if there is some other series that we know converges. And each term of this questionable series is smaller than each term of the series that we know converges. So if I know that this, adding all these things up, still results in a converging series, then if I add things up that are smaller, well, that's going to have a smaller sum, and therefore it's going to converge as well. Now, conversely, if I add a bunch of terms together, an infinite number of them, they're going to diverge if I have something that I know diverges and my new terms are bigger than those of the diverging series. So when I add each of these guys together right here, I know that thing's going to diverge. If I add even bigger stuff together, well, the sum's going to be even bigger, and without a doubt, that's going to diverge. So I'm going to compare a new series to something that I know, whether it converges or diverges. And that's the direct comparison test. So let's take a look at this guy. Does this thing diverge or converge? Well, now let's see. I'm going to think about this guy and see if there's anything that it's pretty darn similar to. If I put a 0 in there, I'd have 1 over 2. If I put a 1 in there, I'd have 1 over 3. If I put a 2 in there, I'd have 1 over 5. And 1 over 9. And on and on and on and on like that. Okay. Well, you know what I know about this thing is I know that if I have a series that looks like this, let me write it over here, n equals 0 to infinity, 1 over 2 to the n. I know that thing is 1 plus a half plus a fourth plus an eighth, and on and on and on and on like that. Now, didn't I see that this converged? Didn't I say that those, if I keep going and going and going infinitely, that adds up to 1? So I guess this thing really is going to add up to 2, isn't it? This series converges. And every term of my new series, this term is smaller than the first term of this one. The second term is smaller than the second term. The third term is smaller than the third term. And so, because 1 over 2 to the n plus 1 gives me terms that are smaller than a known converging series, I would have to say that this series, n equals 0 to infinity, 1 over 2 to the n plus 1, also converges. Because I compared it to something that I knew converged, and each term was indeed smaller. So that's the direct comparison test. Find the interval of convergence for this thing. Well, we're going to talk a lot about intervals of convergence coming up. But my question for you is, does this look familiar? Does this look a lot like which is e to the x? And what's the interval of convergence for e to the x? Well, e to the x, if we look back at that section 11.2, the known Maclaurin series, and hopefully we know a lot about e to the x, and we've taken the time to memorize some of those things. That has an interval of convergence that is all real numbers. So what's this thing right here? Well, isn't this x over n factorial squared? Wouldn't that be like e to the x being squared? E to the 2x? So if this has an interval of convergence, if e to the exponent, the variable exponent, it doesn't matter what this number is. E to any number is going to have an interval of convergence that is all real numbers. So e to any number is going to have an interval of convergence that is all real numbers. So again, that's a comparison. Comparing an unknown to something that we do know something about, and drawing conclusions because of their comparison. Limit comparison test. I really like limit comparison test. You'll notice that there are no x's in this. We aren't looking for any interval of convergence or anything like that. But does this series converge or diverge? Well, for a limit comparison test, again, you don't see any x's here. Keep only the highest powers in the numerator and denominator. So I'm going to take a look at this, and this doesn't have the biggest exponent in the numerator. I've got 2n squared, the biggest exponent in the numerator. In the denominator, that's pretty insignificant. And what is the square root of n to the 5th? I think that we could agree that's n to the 5 halves. And again, we're going from 1 to infinity. Well, if I simplified that further, what is n squared divided by n to the 5 halves? I would have to subtract those exponents. And I'd be left with a 2 on top, and the exponent on the bottom was bigger, and it was bigger by a half. Now again, let's compare this to something we know. Do we know something about p-series? And in a p-series, if this exponent is less than or equal to 1, the series diverges. So something like this, let me get my eraser here. Something like this is going to turn into a p-series. And I've just got to check out, what is my exponent going to be down on the bottom when I simplify this? And if it is greater than 1, I know that this is going to be convergent. And if it's less than or equal to 1, I know that it's going to be divergent. Now, from worksheet 5, whoopsie, missed it. Oh boy, it happened again. That's going to keep happening, so I'm just going to talk about it. Worksheet 10.5, just do question number 5, and then there are some book problems that deal with comparison tests and determining whether or not a series converges or diverges. Now, continuing on, two more things we want to take a look at. Absolute convergence and conditional convergence. Now, let's see, let's come down to here. Let's take a look at that down here. Yep, nope, we're gonna do it up here. If we have a series and we take the absolute value, maybe some of these were positive, maybe some of them were negative, but if we take the absolute value of every single one of the terms, if it alternated, it doesn't alternate anymore. Every single term's positive. If every single term is positive and the series converges, then this series right here is said to converge absolutely. So if we find a series that converges, and then you take the absolute value of every single term and it still converges, that is called absolute convergence. Now, if I have a series where maybe some of the terms are positive, some of the terms are negative, and it converges, but when I take the absolute value, it does not, well, then that is said to converge conditionally. It converges on the condition that some of the terms are positive and some of the terms are negative. But if we made them all positive, it would not converge. So that's called conditional convergence. So let's take a look at example 8. Now, here's what I know. I know that the sine of x to the n over n factorial. I know every single term of this is going to be less than 1 over n factorial. Because the sine is trapped somewhere between -1 and 1. So all of those terms are going to be less than this. And all of these terms, and I should put my exponent there, sorry about that. Doesn't really matter when it's a 1. All those terms are smaller than x to the n over n factorial. Well, what's that got to do with anything? Well, isn't this thing e to the x? So isn't this thing, oh, and I know e to the x converges for all values. It's an interval of convergence, all values of x. So if this thing converges to e to the x, then this thing is going to converge to e to the, not the x, but e to the 1. So this is convergent. And if all of these terms are smaller than that, wouldn't this also have to converge? So this series right here converges. Now, I want to test and see whether it converges conditionally or whether it converges absolutely. So now I'm going to take a look at these terms. Sine of x to the n over n factorial. If I take the absolute value of all these terms, isn't it still smaller than 1 to the n over n factorial? Which I know converges to e to the 1. So even if I take the absolute value of every single term, I'm still going to get terms that are smaller than something that I know converges. And so if I take the absolute value and I get a convergent series, I know that this converges. Absolutely. So the first thing I did is I showed that this converged by a comparison test. And then by taking the same terms, so taking the absolute value of them, I found again by comparison test that even the absolute value terms are going to converge. And so that's how I can say it converges absolutely. Now, alternating series test. Alternating series test for convergence. Okay, remember the nth term test? The nth term test could only test to see if something was divergent. Well, the alternating series test can only be used to determine convergence. It cannot be used to determine divergence. Now, alternating series test is really kind of easy. Alternating series error was really kind of easy. If you've got an alternating series, this thing alternates because we're going to take -1 and we're going to keep toggling that exponent between even and odd. We're going to get an alternating series, plus, minus, plus, minus, plus, minus, plus, minus. Now, we're going to check and see whether this converges. If the next term is always smaller or equal to the previous term, then there's a good chance that that alternating series is convergent. The other thing that has to happen is that as we keep going and going and going, that the nth term, the billionth term, the trillionth term, that as we keep going, the limit of these terms, these keep getting smaller and smaller and smaller and approaching 0. Okay, so the limit of the nth term has got to be 0. Now, keep something in mind. When I'm talking about a sub n plus 1, these things are always positive. This is always positive. It is this thing that determines whether we are adding or subtracting. Okay? But with this thing right here is always considered positive. This is what determines whether it will be added or subtracting. That's what's going to determine that this is alternating. Okay? So do the terms continue to get smaller and smaller and smaller, and is the limit going to be 0? Okay, let's take a look at this. Show that this thing is convergent. Okay. Okay, let's show that that is convergent. Well, now let's see. Now, to show that this is convergent, this is an alternating series. The first term, remember that now n starts at 1. Let me get my red marker here. N starts at 1, so if you put a 1 in there, Negative 1 squared is 1 over 1. And if I put a 2 in there, the top is going to be negative 1 over 2. Next, we're going to have, if n is 3, we're going to have positive on top and a 3 on the bottom. And it's going to keep going and going and going like this. Now, my question to you is this. Is the previous term greater than the next term? I kind of prefer to say, is the next term smaller than the previous term? And the next term, forget about the pluses and minuses. The next term is always smaller than what came before it. So yes, this is indeed true. And is the limit, as n approaches infinity, of 1 over n, remember we're not concerned about the top being positive or negative, we're saying the nth term, always being positive, is going to be this. Is that limit equal to 0? And the answer is yes again. So by alternating series test, this does indeed converge. Okay, cool. But does it converge conditionally or absolutely? Well, what if I took the absolute value? What if I said n is equal to 1 and it goes to infinity, but we take the absolute value of negative 1 to be n plus 1 over n. Now, the absolute value is going to take this thing that makes the terms possibly being subtracted. Everything's going to be positive now, isn't it? And if everything's positive, then this is just like a series 1 over n. N equals 1 to infinity. What do we know about this guy? Well, we know this is a p series. And the exponent on this n down here is a 1. And so if p is less than or equal to 1, this thing diverges. So if I take the absolute value, I get a series which diverges. So by alternating series test, this series right here converges. But I'd have to say that it converges conditionally. Because when I took the absolute value of each of these terms, that did not converge, that diverged. So if it's alternating, we're good, it converges. But if it didn't alternate, it wouldn't converge. And so that's why we have to say it converges, but it converges conditionally. And we have some practice for the alternating series test. All right, so the assignment is posted in Schoology. Good luck.